So it's a pleasure to introduce today to you Jean-Pierre Hubaux. Jean-Pierre Hubaux is a professor at EPFL and head of the Laboratory for Data Security. He has pioneered the areas of privacy and security in mobile and wireless networks and in personalized health. He leads the Data Protection in Personalized Health project funded by the ETH Council. He's also a co-chair of the Data Security Workstream in the Global Alliance for Genomics and Health, GA4GH. He is among the most cited researchers in privacy protection and in information security, and we are very happy to have him today. Thank you, Jean-Pierre, that you take the time for this webinar. Jean-Pierre will present today to us the MedCo project, enabling the secure and privacy-preserving exploration and analysis of distributed clinical and omics cohorts. This project is jointly funded by SPHN and PHRT. It is running since 2018, and we are very happy to hear about the progress of this project today. Thank you, Jean-Pierre. The stage is yours.
Thank you very much, Catherine. Thanks for the nice introduction. Thanks for having me virtually, at least here. So let me start with the rationale of this, of what I'm going to talk about. After talking with many people, I come to the conclusion that is actually known to many people that the current situation of health data management is unsustainable. There are way too many data breaches. There is insufficient and ineffective data sharing, and the ethical approval procedures for research protocols are actually very time consuming and tedious and complicated. Now, this does not have to be the case, right? And with appropriate tools and processes, it can and should be fixed, we believe. These tools should be based on mathematically proven computing techniques that actually already exist, as we will see. And this will give data management the robustness and efficiency it deserves. Let me mention something about ethics committees. So they play a pivotal role in this landscape. So what they do is that they take study protocol and consent forms as an input, and then take into account the legislation, the ethics considerations, and also other considerations such as institutional interests. They produce a go, no go decision, and also some feedback on the study protocol itself, right? So this is a very slow and manpower-hungry, tedious process to check the proposed data protection measures. Of course, they check also other aspects, not only about data protection, but that's here, of course, I'm going to focus specifically on that aspect. And there is a need, of course, to obtain, for legal reasons, to obtain informed consent and a high diversity of consent form with attempts to have a kind of general consent, but this is still an ongoing work, notably in Switzerland. And in the current situation, the ethics committees make an on-paper a priori evaluation with actually little control of what happens afterwards. And actually, this could be changed as well. And there is a risk of race to the bottom in the sense that those of the researchers that obtain more permissions to see data will extract more value, and this will provide them with a more competitive advantage, which means that the areas of the world where there is more protection of the data might be actually at a kind of disadvantage with respect to areas of the world where this is not necessarily the case. So now let me bring also the multi-site studies into the picture. So this is something that is more and more talked about and done also, of course, in many cases. And the benefit is straightforward, at least the rationale, the intuition is that by increasing the amount of available data, it will be possible to increase the statistical significance of the findings. So that's wonderful, at least in theory, but there are a number of challenges, and I mentioned here three, there are more, but they are probably the three that are the most prominent ones. One is the heterogeneity of the data semantics and of the data quality. This is a huge challenge and there are many people working on this, they are doing wonderful work. It's a lot of work, and it's not going to be addressed here. I'm going to focus on data protection, not on data semantics or homogeneity or quality. There is a need to interface several ethics committees and IT services for each of the institutions that are involved, and potentially take into account diverse legislations, especially if one operates in international level. Now, the current approaches for multi-site studies I try to depict them here on this slide. It can be, for example, fully centralized. So in other words, each of the sites is going to provide its own raw data. The data are just de-identified, and then they are provided to a trusted third party, and the algorithm is going to be run on that algorithm, on that essentially centralized database. Now, the data protection in this case, level data protection will be the one that is provided by the security of the central database, right? And each of the sites here essentially lose control over their data. And I put here some examples of projects that operate along these the various techniques. There are many more of those, of course, but just to mention a few, right? Then there is something that could be called the meta-analysis, right? Where instead of providing the raw data, it's more aggregated data that are provided by a semi-trusted third party. It needs to be a bit less trusted in the sense that it's not the full raw data that are provided, but there is a hope with that by aggregating the data, it will in some way protect the data itself. And we'll come back to this in a minute, right? So for one study, we request the aggregated data from each site, but of course, you still need to trust in some way the central server to not misbehave with respect to this data. And then there is the decentralized approach that says, oh, okay, this is too risky. We don't want to have this kind of big central database. Let's go for something in which we send the algorithm to the data. So the algorithm goes from one to the next, and then there's a partial result that is aggregated and then comes back at some point and provide the final result, be it for training a model or for, let's say, using the model for a prediction, right? If it is in the case of machine learning. So now, send the algorithm to the data is something that may sound very appealing, right? And actually is probably the way to go. And the idea is, okay, I send the algorithm to a given site, but implicitly, the picture that people have in mind is that at this site, at each of the sites, there are going to be many patients and few attributes, right? In such a way that the output, which is the outcome of the local computation, the data will be protected just because the individual data are going to be drawn in the mass of the data, right? And so the belief is that the output leaks nothing about the original data, right? Is it correct? Are we sure it is correct? That's not obvious, right? Let's consider another case, which is this one. Assume that instead of having a big, thin, right, tall, thin matrix, we have actually this kind of shape. So we have a situation where there are few patients and many attributes, right? And so the algorithm shows up, and then there is an output. But in this case, it is unlikely that the data is quite intuitive, I think, to see that it is unlikely that the data are going to be properly protected, right? So just to essentially reassert a well-known fact, which is that the communicating aggregate is not privacy preserving, right? And the more time will pass, the more this kind of situation will arise, right? For example, in the case of rare diseases, by definition, there are only very few patients at each institution, right? There may be one or two or three. So then it's hopeless to try to conceal, let's say, to protect the data by aggregating things in the output. Or if you want to do stratification, then of course, in that case as well, if you go to a stratification that leads to small amounts of data per site, we end up in the same problem. Or in the case of genetic data, where the number of attributes is going to grow in a way that is going to be very, very significant. And there again, we end up with a kind of matrix of data that is actually very broad, right? And in the community, something I've already also heard sometimes is to say, well, but at some point, the cloud, the cloud providers will figure out the problem and will provide solutions. But this is not the case, right? Even if each individual institution has its own trusted cloud service provider and uploads of the data there, this kind of issue remains, right? Unless, of course, you accept to put all the data in a big cloud, right? And then the data is there and the computations are made there. But then we are back to square one. Then if we do that, we are back essentially to the fully centralized, right? So this is something that has to be addressed properly, right? So we believe that a kind of technology disruption is needed, right? So if we take the case of locomotives, right? At some point, there was a shift from the steam locomotive to the electric locomotive because it was safer, cleaner, easier to operate and to maintain, and more reliable. And this was made possible by two techniques, essentially. One is the electric engine itself, and the second is the electrification of the railroads. So likewise, our feeling is that there must be a technology disruption for multi-site studies. One cannot just go on with the kind of situation that is existing nowadays and that seems to be very brittle in terms of, so very, very fragile in terms of data protection and very tedious in terms of approving from the point of view of the ethics committees without much oversight of what is happening after approval, right? So the current situation is questionable data protection guarantees, reliance on the manual work of ethics committees, slow other procedures, and the risk of race to the bottom that I mentioned previously. And we believe the future to be techniques, something that is MedCo-like techniques, or MedCo itself, which means relying on two fundamental building blocks. One is secure multi-party computation, and the other one, homomorphic encryption. In order to streamline the approval processes, to rely on mathematically proven data protection guarantees, and to provide really decentralized trust that will pave the way to federated learning. So let me just devote 1 minute to introduce these two characters. This is not a course about crypto, so I just want to convey the intuition of these two techniques. So the first, so secure multi-party computation is, the idea is the basic idea is very simple, is that if there exists a set of stakeholders or players and that they are willing to compute a function that is actually takes as an input the input of each of the stakeholders. So each of the stakeholders has its own input, X1, X2, and so on. And they want to jointly compute outputs, and each of them is going to receive its own output. But this has to be done in a way that none of the stakeholders is able to see the input of the other ones. Right? They just see the output, but they don't see the input, which is exactly the kind of situation that arises in let's say, medical research, right? So in the case of multi-site studies. Right? So there are techniques that in computer science that are mathematically proven and that were established decades ago. And this is called secure multi-party computation, or SMC. The other one is, so just to go through the small animation, you have this here, the function that runs. So I spare you here the 3 hours of painful crypto, and hop, at the end, everyone has to have its own output. In the case, the other building block is homomorphic encryption. So here the idea is that you take two operands, and it is possible to perform an operation on those two, for example, an addition or multiplication or something else, right? And the two operands don't need to be scalars; they can be also matrices and so on. So then you can once you have made the computation, then you encrypt, and you obtain some result, right? You obtain this result. Or you can encrypt separately each of the two operands, and then make a computation on the encrypted version. And if the encryption is homomorphic, then the two values are going to be the same, right? So this enables a fundamental property, which is the ability to compute on the data without seeing the data. Again, a well-known result in computer science that has been around for around 3 decades, and that is mathematically proven. Now, okay, so now MedCo relies on both techniques, right, and combine the two into something that is called multi-party homomorphic encryption. And it comes with 2 features, right? This has been, let's say we said, okay, let's understand the requirements of the biomed community in terms of data sharing. And then let's make use of what is available in the toolbox of computer science. So the techniques that I just mentioned, and then produce the 2 main features, which are first the exploration of cohort, right? MedCo Explore. So the code here has been security reviewed, it has been pen tested, and it is deployed, as we will see in a minute. And then the MedCo analysis, which stands for the analysis of the cohorts themselves, right? And this is under development, right? Rely on a common data model, and we've made it compliant, but it's not restricted to I2B2, right? So it works with I2B2 for the moment, but you could also work with the other models such as Odyssey's OMOP, for example. So the operating principle is depicted here. So the data are taken from the clinical site, right? They are put in the MedCo database, and then from here, they are used in order to enable the kind of the decentralized computations that I've mentioned previously, where the data remain at each of the sites, but the computation is done under secure multi-party computation and homomorphic encryption in such a way that we avoid the weaknesses that we've seen before of sending the algorithm to the data and then hope that actually the outcome of this algorithm is actually is going to be privacy preserving, which, as we know, does not work. So we need to move to the appropriate techniques to achieve this, and this is what we propose in this approach. So a month ago, in spite of the pandemic, and I'm very grateful actually to our hospital colleagues to have managed to not delay the whole process, we managed to deploy MedCo at 3 hospitals, or HG, CHUV, and Inselspital. So it is now installed on their servers, and the first application is in the framework of the SPO, the Swiss Personalized Oncology Project. We'll focus it on melanoma data and also apply to other, let's say, pathologies of this kind. And we are currently also discussing with the Basel and Zurich University hospitals who have demonstrated interest and actually are also involved in the SPO and therefore willing to, let's say, make use of this technology at their premises as well. So let me just show you a few interface examples, just so that you can associate some visual representation of what's going on. So this is for the, as you can see here, for the explore phase. So the user of such a system. So you have to imagine there is let's say a confederation of several institutions that are willing to share the data, but without actually really sharing them, right? So the operating principle that we have seen before, but they were willing to work together. And so there is one researcher who is sitting in one of these institutions that is willing to explore building up a cohort, and then enters a certain number of criteria. So, for example, takes an annotation value, which is a graph for the gene name, and then takes all the zygosities, and then is interested in melanoma, male, and so on. There are a certain number of, let's say, selection criteria. And then based on these selection criteria, the outcome will be that there are actually 273 subjects in the in this community of say hospitals. Right? So then moving to the exploration of the results. So what will be shown here is, for example, the breakdown across the three sites, and then the breakdown by age, and then by gender and by site, and so on. Now, in some cases, some institutions might decide that they are unwilling to unveil this level of detail. They're unwilling to say how many subjects, for example, are at each site, which means that the data will remain aggregated, but there's going to be a breakdown only, for example, by gender and by age, but not by site. So, of course, the tool can be configured in order to meet this kind of expectation. And then we can move to the analysis. So in this case, we are interested, we assume there is an interest in a survival analysis, something that oncologists do very often in order to compare the efficacy of, say, for example, two different drugs. So they do the survival analysis. They select the related group, the time granularity, the max time span, blah, 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 the kind of event they want to consider. And then what they obtain is this kind of curve, which means the survival probability expressed as a function of time, where time is here in the number of days. And so what is shown here is that the blue treatment, in this case, provides a higher chance of survival than the red one, right? And so on. So one can make all these comparisons and then decide accordingly how to move on. And this, as you can see, can be used, as you can imagine, can be used both for research, but also for healthcare, right? In the case one has to make a specific decision with respect to a patient and compare to, let's say, existing similar cases somewhere in the world. So to recap, so the functions that are made available are first, the MedCo Explore, right, which is a secure and scalable system for cohort exploration on distributed databases. So we have seen how it works. So it combines Boolean and OR operators while protecting individuals' privacy and data confidentiality. So here's the researcher. She provides the inclusion and exclusion criteria. The request goes around in the consortium, and it provides back the number of subjects. And so I provide here also the underpinning research papers. So this is for the cohort exploration. For the analysis, so what is done here is to provide a secure and scalable system for statistical queries and machine learning, again, on distributed databases. So here, in this specific example, the researcher provides the list of covariates and the machine learning model potentially, and then this is sent again to the community that is going to provide back the trained machine learning model, right? So this can be used for training, but also for prediction. And so there are statistical functions that can be achieved: descriptive statistics, set operations, cosine similarity, and then linear regression, logical regression are already implemented. We are working also with generalized linear models. And then neural networks is something that we are currently developing. So let me focus now on those two, linear regression and logistic regression. So just to make sure that everyone is on the same page, let me remind something that most of you already know. So assume there are a certain number of observations, and we want to find the line that fits best these dots, right? So generic method to achieve this, to find the best coefficients B0 and B1 of this line, is the gradient descent, right? And that is depicted, let's say, on this here on the right. And this will make it possible to find this line, right? Now, if, however, so this works fine. So here we assume that all the data are available in clear text in the same place. But that's too easy. It's not interesting, right? It's not the kind of setting we are considering here. If this is not the case, right? If the data are actually in different places, then, for example, assume that the 6 dots have been separated, are actually now in 3 different places. So the first stakeholder has, or the first server has the first 2 dots. The second has dot 3 and 4, and the last has dots 5 and 6. Of course, it's a toy example. Huh? Then, of course, their vision of the world is quite different, right? And this is depicted here by this gradient descent operation that can lead each of them, each data provider, to a conclusion that is actually suboptimal, right? That is diverging and suboptimal, because they are operating here in actually separately. They don't leverage on the common knowledge, right? So to avoid this, what is needed is to work together, right? And this is what is shown here. But this is done unlike, let's say, the conventional distributed or decentralized gradient descent. This one is actually secured, right? So here, the query defines a query, for example, training of a linear regression model on specific attributes. Then the request goes here. The local model is going to operate at each, let's say, to function at each of the places. And then there is going to be the DP, so the data providers are going to collectively and iteratively combine their encrypted local model in a global model, right? So there's going to be as many iterations as needed. And then after the training, and based on a given pre-agreement, the model is either kept secret for oblivious predictions or revealed to the querier. Again, it will depend on the policy that is used in such settings. Now we have made some benchmarks to check the accuracy, right? If we move from, what is interesting is to see when moving from centralized to decentralized and then to secure decentralized, aren't we taking the risk of losing in terms of accuracy, right? And experience shows, so this is shown actually on these plots, where you see here for 3 studies. So the first 2 are logistic regression on medical data, PIMA, so PIMA, Indian diabetes, and the other one is breast cancer, Wisconsin. They are typically typical, let's say, data sets that are used in such settings. And the third one has nothing to do with health. It's actually the famous MNIST, which is the recognition of handwritten characters, right? And you have the size of the data set for each of those, right? So what we see here is that we have the accuracy. In the case of the centralized, of course, centralized obtains the best result, right? The independent training is less good because it does not leverage on the collective knowledge of the different sites, right? And therefore the red is systematically lower. But the good news is that the distributed not secure, and which would be the one where sending the algorithm to the data, but without making protections, or in the case of MedCo analysis, actually obtain as good an accuracy as the centralized model, which means that there is no loss of accuracy when making use of these kind of techniques. So this is one concern. What happens with the accuracy? The other concern is how about performance, right? Homomorphic encryption and secure multiparty computation. I mean, these tools have the reputation of being slow, of generating much overhead, right? So here again, we made some benchmarks because we brought a number of optimizations to the system, and we also leverage, of course, on computers that are way more powerful than was the case still 5 or 10 years ago. And things become possible, really possible. So here you can see data, let's say numeric results for the case of logistic regression with 5 data providers and 25,000 records with a 128-bit security level, which is already a pretty high security level. And what is plotted here is on the x-axis, the number of features, or covariates if you wish, right? And on the y-axis, the runtime that it takes on machines of this characteristic. They are just relatively powerful, but nothing really fancy, off-the-shelf machines. Right? So what we can see is that with this already quite big data set, we see that as long as the number of features remains up to 256, which is already quite a large number, the runtime is in the order of, let's say, 3 minutes, right? When we go beyond that, then beyond the point that is called maximum threading, then it reaches essentially the parallelization limit, right? And from this point on, then the execution time increases linearly, or more or less linearly, with the number of features. Well, which means essentially, from the performance point of view, yes, it takes its time, but it's much faster, say, than the time it takes for an ethics committee to make a decision, of course. So if this is a way to fuel the whole process, then it would certainly be a tremendous improvement. Then that's another, let's say, slide showing additional benchmarks that we made in terms of MedCo performance. In this case, what is shown here is the scalability with respect to the number of data providers. And so what is done is that we keep the amount of data per data provider constant, but we increase the number of data providers. And we see that just because we can leverage on more available computing power, essentially the runtime remains more or less constant. And this shows, let's say, similar results. So one additional thing that needs to be taken into account is the fact that the system has to protect itself also against legitimate users or someone who has stolen the credentials of legitimate users. And for this purpose, it is important to, let's say, implement something that is very similar to what already happens nowadays in the hospitals, which is the systematic logging of the queries, right? So for this purpose, a blockchain or distributed ledger can be very useful, actually. But the kind of blockchain that we use is actually not the one that is found in Bitcoin, that uses actually public blockchain. We use a closed blockchain that is completely managed, is much simpler to operate and also much easier to control. This provides an immutable log and is a kind of deterrence from misusing the system, because people will know that every, let's say, queries are going to be logged and can be collectively checked. Now, an additional dimension to this landscape is quantum computing. As we know, billions of dollars are invested in producing quantum computers. When these computers are going to become available, it will be great, because they will help solving a number of problems, including in biomed. But they are going to have a side effect of breaking much of the existing cryptography. And if we're thinking now in terms of long-term protection of the data, right, medical data, genomic data, that has to be protected over decades, it's time to start thinking also in terms of the advent of this kind of technology. Right? So for this purpose, we have developed library that is based on lattice crypto, lattice-based crypto, that is a kind of crypto that is actually resistant to a quantum computer because of the nature of the operation that they rely upon. So I don't want to bother you too much with this, but you can find more details on this in case you are interested. So what we are doing is we are introducing this kind of technique in MedCo as well. Well, so to wrap up, these are, as we have seen, the features and guarantees that are provided. So in terms of functionalities, the descriptive statistics, set operation, causality similarity, and then the things mentioned underneath, so generalized linear models, the neural networks on which we are working as well. In terms of data security, the data never leave the data provider's premises. I think this is a very important property of this kind of approach. And the intermediate computation results are always protected. And in terms of privacy, the query only sees the final result, right? Now, in terms of timelines, this is taken directly from the MedCo website. These are the next steps. So we're currently working on bringing MedChain. So MedChain is the technique that I mentioned previously into the system and have it fully integrated by Q3. And by Q4, the idea is to produce the so-called MedCo v3.0, which is MedCo analysis that will enable privacy-preserving training of machine learning models. Training and, of course, also the ability to do prediction with these models. Now, let me say one word about the position of MedCo within SPHN to see exactly how it fits. So in the current SPHN model, there is, the first step, there is a federated query where, so all data are in clear text at the hospital, the patient count per hospital in clear text, and there needs to be a central trusted party for the count aggregation, and only clinical data can be queried, right? So then, based on this kind of first investigation, so the feasibility analysis, then comes the ethics approval, that of course takes its time for good reasons, right? So here we are talking about potentially months, right? And then there is a project data analysis, which is the raw data access and analysis, right? That requires, of course, DTOA and ethics approval. With MedCo, then we move to the SPHN model enhanced by MedCo, then this leads to the secure federate query, right? Where the clinical data are still in clear text, but genomic data is encrypted at the hospital. So here comes the genomic data, right? The patient counts per hospital are encrypted, and there is no need of a central trusted party for counts aggregation, right? And one can really operate also on the genomic data. Then one can go via the MedCo road, right? That should be fast, because then we are relying on a tool that provides a certain number of guarantees, where there is controlled federated data analysis. And one can achieve low to medium complexity statistics and ML, right? And the encrypted data are at the hospitals or in the biomed IT node. And one can leverage on or benefit of a streamlined DTOA and ethics approval, because there is a standard, let's say, platform that provides a certain number of guarantees. In some cases, that might not work, because in some cases it is still needed, it is still necessary to check the raw data, or maybe the level of computation becomes so complex that actually it is not possible anymore to do it on this kind of platform. And in that case, one should go the more traditional way, but then it will go require again the ethics approval. Right? So depending on one, so the hope is that most of the studies will be able to go to the left, and in some cases one will still have to go to the right. To facilitate this process, we have produced a document that is meant for essentially the legal specialists, for the readers, for the ethics committees, and for the people in charge of data protection in hospitals. Is something like 20 pages that is really specifically taking into account the Swiss legislation. So this, we are actually very grateful to Valérie Junot of the Faculty of Law in Geneva, who's working also in Lausanne, who has helped us formulate things for us autistic computer scientists in such a way that it can be understood also by another community. Voila. Let me also mention, I'm almost done. Let me also mention the SCOR project, the Secure Collective COVID-19 Research. So some of our colleagues in the US have heard about MedCo, and they said, okay, this is fantastic tool. Why don't we make use of it in such a way that we deploy it and use it in order to address some of the challenges of COVID-19, right? So the purpose here is to prove that it is possible and faster to advance in this kind of research for epidemics by obtaining world-scale meaningful insights without compromising patients' privacy. And here you have the URL if you want to know more. This is a relatively recent initiative, as you can imagine, right? Let me also mention that we have also other international collaborations with the I2B2 Foundation, with the colleagues in Boston, the G4GH, the 1+ Million Genome Project in the EU, and also our neighbors in Tübingen and many others that are not mentioned here. Let me also mention the main source of our funding, which is actually the DPPH project. That is a consortium that brings together FI Vienna, who is very active in the ethics around medical data. There is Jacques Fellet, a geneticist at EPFL in CHUV, a close collaborator, Brian Ford, here in the School of Computer Communication Sciences. And there is also the Swiss Data Science Center, who in the more long run might also provide a platform for this kind of solutions. Well, and we are, let's say, this started in April 2018 and will run until the end of next year. Let me conclude. So we believe that the current situation of multi-site data management is unsustainable, and that much of the solution is to be found in multi-party homomorphic encryption, which means doing two things. First of all, is to perform computations without seeing the data. That's what homomorphic encryption provides, and rely on decentralized trust. And this is what secure multi-party computation provides. And the hope is, and we've talked with several people who tell us that it is actually meaningful to believe this, is that such a systematic approach will streamline the approval processes by ethics committees. And of course, they provide mathematically proven data protection, which is something we believe is missing nowadays. So we've deployed at 3 hospitals. We will soon, we're already starting to use it for the SPO and for the SCOR projects. It's fully open source. So if you have nothing better to do, you may want this evening to take a close look at the code. One limitation is that, as mentioned, computations can become very heavy for some operations. So it does not necessarily solve all the kinds of computations we want to do. But the more progress we make with MedCo and also working with other researchers in the world who are bringing, let's say, libraries of this kind, the more it will be possible to actually make computations under this kind of protection. Well, let me also thank all the people I've been working on this topic, especially David Freudicher, Jean-Louis Reisar, and Juan Troncoso Pastoriza, who helped with some of the slides, but of course, any possible mistakes are mine. I thank you for your attention. I hope that we now can start some kind of discussion. Thank you very much.